All right, it's the top of the hour. I think we're ready to start the workshop. I'm going to leave my video camera off this time because I want the bandwidth for things I'm showing. This slide that's showing on the screen right now is the slide for a tool that we use for these workshops. We also call them PMM hackathons, which is why you see that PMM hackathon all over the place. So this tool allows you to get on a machine that has Optane persistent memory installed. Each person who clicks the request access and types in the workshop ID gets a username and a password. If you haven't done that already, I suggest when you do it, write down the password or take a picture of it with your phone or something, and I will leave the server up with these accounts that you're creating for yourselves active over the next week. So even though this workshop is only 2 hours, please feel free to fiddle around with the examples or even write your own programs from scratch that use persistent memory and try them out on this machine. I'm going to go through a few slides that give you the basics, kind of the necessary background, and I'm going to then walk through a couple of examples, one in C and one in C++, again, just to kind of show you how the examples work and give you some basic background. And then we have Steve Dorman, who's co-teaching this workshop. And we've had a lot of interest in the Java support for persistent memory. So Steve has added a lot of pretty interesting examples to this workshop for Java. And so after I get through the fairly short C and C++ examples, I'll turn it over to Steve. And the rest of today's workshop will be on the Java part. But as you'll see, there are a lot of examples in the workshop that we're not going to go through today because it would take us a couple days to get through them all, and so please feel free to explore yourself. So I'm going to go back through the slides now, but if you forget this URL or the workshop ID PMDK, I'll put this slide back up in a minute. So now let me just kind of go through the basics, the background that you need for the workshop. Everything that I show you in this workshop, including these slides and Steve's slides and all the examples, are stored permanently on GitHub in a repo named after today's date, 2020-06-25. So this URL is really the only thing that you have to remember, because everything I show you will be there if you ever want to refer back to these examples. I'll leave it there as reference forever. It's kind of frozen in time. And this URL also appears inside the tool once you get logged in. At the very top, there's a link to this, so that you'll have plenty of opportunities to get back to that GitHub repo, and I'll show you that in a second. I also want to point out that the book, that you can find a link to it on these slides, but also just go to pmm.io and you'll find a link to it. The book covers a significant amount of the material that we're going to talk about here. It's free, and I highly recommend it. Steve Scargill did a great job pulling together all this material, writing up a lot of details, and making sure that this is a very approachable way of learning about persistent memory programming. So what I'm going to do is, like I said, do these essential background slides and then get you hands-on as quickly as possible. So the tool is sort of set up like this. Here you are sitting at home with your computer, your laptop, or whatever, and you go on your browser to pmmhack1.pmmhackathon.io, and each one of you, when you log in, you get your own username that is of the form pmmuser and then a number. And when you log in, I put you each in your own Docker container, just so that you're kind of isolated from each other. But all those containers are using the same persistent memory file system that is exposed inside of each container. And so I guess that kind of shows you that persistent memory works inside of Docker containers, which it does. So the first three examples that you'll find when you get in there are marked with this little recommended yellow tag. because they're very basic, and we're going to go through 2 of them anyway. But they are really good for giving you some essential background. But there are, like I say, there are a lot more examples. And there's a little hamburger menu at the top, which actually I'll just go ahead and show you. So if I log myself in, I'm PMM user 1, and I give the password that I was assigned, you can see at the top, once you get logged in, there's this little hamburger menu here that can always get you back to the slides. It can always look at your copy of the repo, because in this tool you're allowed to update the examples, so you get your own copy. And also you're allowed to get a shell window, and I'll show you how that works in a moment. But the hamburger menu is on every page. It's an easy thing to get to so that you can get back to these things. And not only is there a browser-based shell window that you can use, but you're free to SSH into this machine with the same credentials that you'll get. So if you're a person who doesn't like to be doing things in a web browser and you just want to run SSH, please feel free to do it. You'll just find yourself at a bash prompt in your Docker container. In the Docker container, the path to persistent memory is /pmem. So it's mounted inside your Docker container as /pmem. So it's pretty easy to find. And I just want to point out that this tool is meant for a friendly workshop. If you want to prove to me that you can bring this server down to its knees by causing a denial of service attack, you probably are right, and I'll grant you that already. So please be friendly. I don't currently have any quotas on how much CPU or persistent memory you use. So hopefully that won't be a problem. It hasn't in the past. Okay, so now let's get into the more interesting things. So there are a lot of ways to use persistent memory, and you've seen presentations about a number of them today. First of all, the storage APIs, well, they just work. You can set up persistent memory to look like an SSD. Or you might have a library or even the kernel that's using persistent memory transparently, and your application has no idea that it's doing that. The Optane product also has a mode called memory mode, where it just uses persistent memory to make the system's main memory look like it's huge and it's still volatile. There's nothing persistent about it in that mode. And so those 3 modes are kind of too easy. There's really nothing to cover there. There's nothing to change in your app. I just want to make sure you're aware of them. What we're here to talk about today is when you really want to exploit what persistent memory can do, and you want to write a program or modify an application to use direct load store persistence. As you see on the presentations today, the slides about PMDK. PMDK is all about making that easier. So we're gonna give you direct access to the persistent memory. We're going to show you code, but also talk about the concepts. But these are just starting points. They're just examples. And it all starts with the programming model, which if you've ever looked into persistent memory at all in the past 5 years, you've seen this diagram probably too many times now. But the programming model is very, well, it's actually very simple. The whole idea was not to create interfaces until we absolutely had to. So instead of coming up with a new way of naming blobs of persistence, or instead of coming up with a new way of managing the permissions, we make these things show up like files. And that's what you're seeing here on the right-hand side here of this diagram. When an application opens up a file on a persistent memory-aware file system, all the standard file APIs work. But when it memory maps that file, instead of mapping into the page cache like you would do for storage, you're getting this direct path, which we call DAX. And that's this arrow on the right, where an application can do loads and stores directly to persistence. So don't forget that the programming model starts with the storage APIs, and that's how, you heard earlier Piotr says he does all of his development just on his laptop because the storage APIs work. And PMDK detects when you're just using the storage APIs and just uses them. So you're fine to just use those for development. In this middle path that I show on the programming model, like I said, this is where persistent memory just looks like an SSD. So it's not very interesting for today's class, but I just wanted to kind of point out that that is a supported model. I didn't set this up on the machine in the Docker containers because we're here to talk about the rightmost path. And in the rightmost path, persistent memory kind of also looks like an SSD. I mean, all of the same APIs work. It's just now there's no caching because there's no reason, there's no page caching. There's no reason to bring in a block from storage into the page cache. like there is for traditional storage. There's really no other way to do it. But since persistent memory is byte addressable, even if you're going through the file system, you can see this arrow that's kind of right here in the middle of the file system. The file system is free to talk directly to the persistent memory. And then, of course, you can see the arrow on the right where the application is free to talk directly to persistent memory. So all these APIs that I've mentioned so far are completely standard, right? On Linux, these are the POSIX APIs. On Windows, they're the 30-year-old Win32 file API. They've been around forever. And we really don't introduce anything new in the programming model until you try to do something what we call optimized flush. Now, traditionally, if you memory map a file and you store some data to that range that you memory mapped, you don't know that those stores are persistent until you flush it. And on Linux, the call to do that is msync. And on Windows, it's called flush view of file or flush file buffers. And so you have to do that step if you want to make sure that something is persistent. And that's still true even for this picture, for persistent memory. But since there's no page cache to flush, what does the kernel actually do? When you call msync and tell the kernel that you're ready to flush, what does the kernel actually do? Well, it just uses instructions to flush the CPU caches to make sure that the data made it all the way down to the bottom here. Well, those instructions are not privileged. They don't have to be run by the kernel. And so we introduced an API, which I call optimized flush, in order to allow the application to do that directly without the call into the kernel. And I'm going to show you that API in a minute. Okay, so today's focus is going to be on the right-hand side of that diagram. And remember, the persistent memory in your containers, in your Docker containers, is mounted as /pmem. That's where you'll find it. Now, I did put a slide in here on how the hardware works. I'm only going to very briefly touch on it here because, of course, the whole point of using libraries is so that you don't have to worry about a lot of these details. But the main thing you do have to know is that when you do a store, which is called a move instruction on x86, it typically goes into these CPU caches that I show in the left up here. And, you know, we'd love to just say now it's persistent. But those caches are pretty big, and if we wanted those caches to be persistent, we'd either have to make them right through caches, in which case you wouldn't get the performance benefit from these huge CPU caches, or we'd have to make sure that even if you lost power, these caches get flushed, and that would require quite a bit of stored energy, like a battery inside the machine. So instead, we make it the application's responsibility to flush these caches, at least on current machines. Maybe later, we'll have machines where these are persistent. And once they're accepted by the memory subsystem, that's what this kind of trapezoid shape is here, then they're considered persistent. So even if the store doesn't make it all the way out to the media, the platform that supports persistent memory is required to implement this small red dashed box here. It's required that even if you lose power, anything that made it into that red box is considered persistent. It'll get flushed automatically to the media. So that's how every platform that ships persistent memory today works. There are some other application responsibilities regarding flushing than I just showed you. For example, the application needs to understand what instructions are available on the machine that it's running on. And so I drew this little chart, and it's in the slides. You can look at it if you like, but it's kind of a pain to program. You have to do a lot of these CPU ID instructions to detect what the platform supports and so on. And it's very boilerplate. If you've written this routine once, then you would just use it over and over again. So of course we put it into PMDK, and you don't have to write it. And in fact, I would recommend you don't write it because you might as well use the one that we wrote and tuned and debugged. So I'm just sort of showing you this is the kind of thing that PMDK is going to do for you. Similarly, there are some application responsibilities around recovery, like what happens if the flushes that I talked about earlier that happen on a power failure don't happen correctly, or what happens if you get an uncorrectable error. And PMDK also handles a lot of that for you. But the biggest thing that you have to worry about as an application programmer is consistency. So here I am, in this little example. You've seen this in one of the slide presentations today already. I'm opening up some persistent memory. I'm writing a string to it, and I crash before I can flush the entire thing. And the results are all over the place of what you might see because flushing is not a transaction. Flushing just says, write out anything that hasn't been written out that's in the caches that's dirty, but it doesn't do it transactionally. So that's really up to the application, and that's why we made libraries. And even if you use my optimized flush, which we call PMM_persist, it's faster, but it's still not transactional, right? So that's important to understand. So this is why we wrote the libraries, the Persistent Memory Development Kit. I think you already know quite a bit about it from the earlier presentations. Piotr put up this slide here that kind of walked through them, and so I'm not going to do that now, but I am going to point out that I'm going to show you a quick example of just using persistent memory directly and then using it with the PMDK. I'm going to show you this PMMKV example, which is a very high-level example where the library basically does everything for you, and you only have to worry about loading and storing keys and values, which is very nice. And then we'll get into, yeah, go ahead.
So the question came up I thought will be right to answer right now. So the question is, if multiple applications are running, how do you prioritize who gets to flush first?
Oh, interesting. Yeah, so that's a great question. So I kind of have two answers. One is the software answer, and then one is the hardware answer. So if multiple applications are running, of course they're scheduled by the OS, and if they're competing for resources, then that's an OS responsibility. And performance critical applications are often tied to their own CPUs and so on. So that can give one application some amount of priority over another one. At the hardware level, the hardware is traditionally not aware of different processes, different applications, and so it's really kind of first come, first serve. Of course, what in practicality happens is they compete for bandwidth, right? Because Optane media is a little slower than DRAM. If you're going to get bottlenecked by the media, it's going to be because you're waiting on bandwidth. And so we do take measures in the hardware to try and keep, for example, one processor from starving out another processor. But they are all ultimately competing for bandwidth. As long as there's plenty of bandwidth, there's no problem. All the flushes happen at the same time. But if you're bandwidth bound, then there's maybe back pressure, and you may wait for your flushes because of the media speed. That's a great question.
Thanks, Andy.
Yeah. Okay, so as I said, I'm going to show you this PMMKV example, and Piotr kind of talked through these libraries a bit, but in that PMMKV example, I just thought I'd kind of show you the path that we'll be taking. The PMMKV library is built on the concurrent hash map that you've also heard about today. That's built on top of libpmmobj, which provides transactions and allocation. And the PMMobj is built on top of libpmm, which handles very basic things like flushing and copying data. So it looks like a lot of libraries, right? It looks like a lot of code, but actually it's a very simple path that you're taking here, just using what you need. And the real challenge is, how can I put this code in here where that PMDK red box is? How can I put that code in here to help you write your application without loading you down with a whole bunch of layers of code? So you're going to hear a lot about that in all the examples, especially when Steve gets into his Java LLPL examples. He's very conscious about the amount of software that you have to run, the number of instructions that you have to run for each operation. Okay, so once again, if you haven't already logged into the tool, now's a good chance to do that. The URL again is pmmhack1.pmmhackathon.io, and the first time you click on this little request access link that's on the main page, and it'll ask you for a workshop ID. You type in PMDK, and the workshop ID, PMDK will give you your own username and password. Take a little picture of that password with your phone or something in case you want to log in again later. And again, I'll keep the accounts around for a week so that you're free to continue playing. So I'm going to go ahead and switch to my browser now and go through the first couple of examples. So here I am, I'm already logged in. And you can see at the very top is a link to the repo with all the examples in it. I'll just click on it and show you. It's on GitHub, and you can see every PDF file here. These are slides. The ones that I just showed you are in slides.pdf. Slides about the Java LLPL library are there, but we also have several other deep dive slides if you're interested. But in the examples directory are all the examples, and you're going to see those firsthand. So I'm going to go back to the tool. But just remember this date here. This is where we stored today's content permanently, so you can always get back to it. So I thought I'd start with the most simple example I could come up with. So example A is just about how to map persistent memory. And so I'm going to click on this, and you can see the way the tool works is in the example, you sort of scroll your way through it, and it explains what you're looking at. And so here's my picture again of the programming model, but we're going to just use the programming model without any PMDK, just the simplest thing I could do, just to kind of make sure everybody understands what DAX is about and what mapping files does for you with persistent memory. You can see I just sort of drew this picture again of that direct access that I'm going to get from the application by calling mmap. And to flush something, I'm just going to use the standards APIs. I'm going to call msync. Later on, there is another example. You're free to look at it whenever you like. Example F does the same thing using the library, using libpmem, where you can see it's a little cleaner. But here the example is just meant to be very basic. Inside of your Docker container, like I said, your persistent memory is mounted using the path/pmem. And you can see if you were to get a shell and go inside your Docker container and do a df, you would find the persistent memory there. In fact, I'm going to do that right now just to show you how the shell feature works. If you're not a browser window type person, you want to get in there and get your hands dirty, you can see I give you a shell just by selecting it from the hamburger menu, and you're sitting there right in the same example directory. This is example A that we're looking at right now. And so if I do a df of /pmem, you can see I've got access to 1.4 terabytes of pmem here as /pmem there. And I can see a lot of you on my monitor here are testing this out and logging in. That's great. So it looks like it's working. So I'm going to go ahead and exit the shell session and go back to my example. But the other important thing is if I type mount, you can see that the file system is mounted with the DAX option. That's what gives us direct access when we memory map a file. Okay, so now I'm going to scroll down and actually look at the program itself. Now I tried to, in these examples where I'm using APIs that have man pages online, I tried to link to them so you can click on these little things and get to those man pages. But this example is very basic, and so I'm just going to put the code right here in front of you. And the way that this tool works is this is not just a window for browsing the code, but it's an editor. So if you want to try and make changes and see what happens, you're free to do that. So this is a very simple C program. It takes a file name as an argument, and that's meant to be a file on the persistent memory file system on /pmem. You can see on line 20, it opens the file for reading and for writing. And then on line 23, it calls mmap. So this is a very basic mmap call here. I'm not really showing you anything out of the ordinary. This would work for any file. And what's important to know is that there's an extra flag to mmap that you use if you want to be able to use the optimized flash. I'm not showing you that here because this is such a simple example. We're just using the standard API. But PMDK knows about the special flag, and we describe it in detail in the book. Once I have it mapped, I should just be able to write to it, like say, hello, persistent memory. And I'll even show you, I can modify this from Andy. So this is just to show you that this is also an editor. And then I can flush the changes with msync and print the word done. So that's the entire example. I'm just writing that string to persistent memory. If I go down a little further now, I can build that. When I click this green button, it actually runs make on the server and builds it, and you can see it running the C compiler here and basically compiling it that. If I had made an error while I was editing up here, I would see it in the build output right here. So if you're editing these files, make sure that the build works cleanly before you go on. And now I'm just going to run this. Now the way that I've set it up for you to run these examples is you provide a little shell script, which I write for you here. And so in my shell script, I first start by making sure there's no leftovers from a previous run. I create a file of 1 megabyte in size /pmem. So there's the file being created by, on Linux, you can create a file, just an empty file full of zeros using the truncate command. So that's how I'm doing it. On Linux, there's also a program to dump things in hex. That's what hex dump does. So I show you that initially the file has nothing in it. You'll see that in a second. Then I run my example, and then I show you what's in the file after that. So some pretty simple steps. Now you can edit this file too. So be careful if you put in this file rm-rf star. It will delete all your files when you run it, but you can put whatever you want in here. I don't check it. So here I am. I'm going to run those things. My little running program prints a plus in front of everything before it runs it. So you can see that it first created the file, and then it ran the hex dump command. And this is what the hex dump command prints if the file contains nothing but zeros. It just prints that row of zeros and then a star telling you that the rest of the lines match. So there's nothing in the file. Now we run example A here, and then dump it again, and sure enough, you can see, hello, persistent memory from Andy. So we did write into persistent memory and dump it out. So this is an extraordinarily simple example. In fact, it's so simple, it's not that useful. But I just wanted to show you the basics of what it means to memory map a file and use it as persistent memory. Everything that I'm going to describe now is built off that basic premise. The machine is obviously running Linux, and these are Linux commands. I did put a link here, in case you're interested, at the end of example A to a Windows version of the exact same program. And the book contains both Windows and Linux examples. So you can take a look at those. So that is the simplest example I could come up with, and probably the lowest level example I could think of, where nobody's doing anything for you. You're calling mmap and you're getting a pointer to a bunch of persistence, and the rest is on you. What about kind of the opposite end of the spectrum? What's the highest level, easiest API that there is to use? And that is undoubtedly our libpmkv API. So example B is about that. So I'm going to go into example B. Now, example B is, as you'll see, it uses PMDK to speak in just keys and values. And now key value stores are really popular. They're all over the place. I think I Googled around for key value stores and came up with, hundreds of hits. There's so many libraries out there. So why did we write another one? Why is it interesting to write a new key value library for persistent memory? Well, typically a key value API looks like this little cartoon that I drew here. An application wants to look up a key and get back a value, for example. And so there's some logic in the key value library that knows how to find it. It finds the value based on the key that you've passed in. And then it really has no choice. This stuff is on storage. So to give you the value, it has to copy that value up into your buffer, right? That's pretty much, every key value API out there is buffer-based, right? Because that's how storage works. There's no way for you to go directly to the storage and start messing around with that value, because storage can only read blocks and write blocks. In order for you to get to that value, which is some number of bytes, it's going to get copied into a buffer. But with persistent memory, we have a new way of looking at a key value store. Now when the application looks up a key, it can just return a reference to that value, just a pointer. And now the application has direct access. There's no data that moved around. So if the value in this case is, a 2 gigabyte cat video that you're looking up, you just access that cat video in place instead of copying the 2 gigabytes into a buffer that you'd have to do with a traditional key value store. So you can see that that's one way that a persistent memory resident key value store can really exploit what persistent memory can do. Persistent memory is byte addressable access in place persistence. That's what's so cool about it. And I just drew this diagram here to kind of show you an example of how all the pieces fit together. I also had shown you on the slides. But it's kind of important to see how each layer does a little bit of the job. But even with all these layers, with the PMEM in there and the PMEM OBJ and the CMAP engine and everything, the app still got that direct access, right? Once it got this pointer here to direct access, it's looking at the data by just doing load instructions. There's no API calls after that, right? So the API calls were just about finding the value or changing it or deleting it, that kind of thing. But once you have access to it, you're accessing it right out of the persistence, which is one of the cool things about persistent memory. Okay, so now we're going to get into the PMDK. It has various bindings, language bindings. We support C and C++ and Java and JavaScript, and yeah, I think there's a Ruby binding and so on. There's actually quite a number of bindings. I'm going to use C++ for this example, and I've put the example in two files. One is called kvinit.c++, this file here, and it just provides this less interesting logic here to either open or create a file that contains the key value store. So you're free to look at that on your own, but it's just the thing that decides if the key value file is already there, then open it, otherwise create it. So I call that must open or create because it'll automatically check for errors and exit if there are any errors. So it kind of cleans up this code quite a bit by just putting that in a different file. And then you can see I wrote a little helper function here on line 17. I call it kvprint, and if you call kvprint and you pass it a key, which is a string, and a value, which is a string, then it's just going to print it to the output. It's going to print out the key and then an equal sign and then the value in quotes. So this is just a handy little print function that I'm going to use later down in my example. Now the way I arrange this example to work is you can run it in one of three ways. If you run the program and just give it the name of the persistent memory file, then it won't take any actions, it won't modify that file at all. It will just print out everything in that file. It'll find all the keys and print them out with their values. So it'll call that kvprint routine that I just showed you for everything that's in the file. If you run it with an extra argument, you say pmkv and give it the file name, and then give it just a key, then it'll just look up that one key and print out the value. Or if you give it yet another argument, the file name, the key, and the value, then it will add that key value pair to the file. So this is just a quick way for me to make this into a very clear test program where one program can do all three of these things. And I can just show you how the API handles this. So let's get to the interesting part. If argc is 2, then someone has done this case that I'm showing on line 26, where they just gave me the program name and the name of the file, the persistent memory file. So you can see the API in the PMDK is pretty simple. You just call get all, and for every key value pair that it finds, it calls this little callback function. And so it'll call kvprint for each one of those. Okay. Now with an extra argument, again, I'm going to now look up the key. And so that's just called get is the API. But instead of calling kvprint here, I wanted to illustrate another very common thing that we do with these C++ language bindings for persistent memory. And that's this thing that you see on line 50. See this little thing with the square brackets and the ampersand there? That's a lambda expression in C++, which is a nameless function. And it's nice because you get to just put the function right here to do what you want it to do once you get the value. So this get call on line 50 is going to get whatever the key is that you passed in. It's going to get the value, and it's going to call my little nameless function here with that value. And inside this function, I get to operate on that value and do whatever I want. And the reason why it's kind of cool is that this function is inside the scope of this outer function. So it gets access to these local variables and things like this too. So I get to write it as if it's code that's right here in the function. But you can tell that you're actually inside a little subroutine here. And when you fall off the end of it, then the key value store is able to release any locks that it has on that value because it knows that you no longer are using it. So it's a nice way of giving somebody control and then getting control back after the little lambda function exits. And again, you can see all it's going to do is print the key and then the value that it found. And then finally, here's the version where we're actually putting a value in. where someone has given us an argument that is the key, an argument the value, and you can see the API is put. So you can see that they're pretty basic. The three operations, get all, get, or put, are the basic operations of, well, any key value store. And that's true for lib PMDK as well. So I'm going to go ahead and build this. And of course, you're free to build or modify and build your own version of it in the tool. And so now I have this binary called PMDK, and I put in here a little reminder of the three different ways you can call it. But you can see I wrote a little test file here where I set a couple of keys, Bach and Mozart, and I set them to the value of their lifetimes. And then I try just running it with just the name of a key so we can see if it looks up the value. And then I added some more, and then I run it without any additional arguments, and it should print everything. So I'm going to go down and just run the script. Okay, and then sure enough, you can see first it set the values. When I looked up the key Bach, I got back the value, set a few more values, and then when I called it this way, it traversed them all. Now notice the order here is not necessarily the same order that they got inserted, right? And that's because the map that I chose to use in our program is an unordered map. So you can get back these keys and values in any order. We have an ordered map also available. That's part of the PMDK. I just am not happening to use it right now. But you can look on pmm.io for all the maps we have available. Okay, so that gives you kind of a quick example of a key value store, a very, very high level, very easy way of using persistent memory. If you can store a key and a value, then you can look it up, and you really don't have to worry about anything else. Note that the key value store is always consistent in the face of failure. You can crash this program here between any two instructions. The machine can have a power failure. You can crash your program. The OS could crash or hang, and the key value store will still be consistent in persistent memory. That's what you get by using the transactions that we have in PMDK. Now, if you go back to the list of examples, like I said, there's a whole bunch of other examples, but if you scroll all the way to the bottom, you get to example L. Example L is where all of the Java LLPL examples are, and that's what we're going to go over next. So what I'm going to do is turn this over to our Java expert, Steve Dorman, and let him take you through those examples. I'm going to go ahead and stop sharing my screen and give control to Steve. There we go. And Steve, you are welcome to take over.
Okay, thanks, Andy. Let me get my slides up.
So while Steve is sharing, Andy, there were some questions.
Oh, sure. Yeah, go ahead.
Okay, so the first one is there ordering semantics that we have to worry about, for example, using mfin?
Yeah, boy, that's a great question. Of course, there are definitely ordering things to worry about because, for example, you don't want, if you're setting a bit that says I completed this transaction, I added, $10 to somebody's bank balance, you don't want that complete bit to get sent out first. And this is very important because people are used to doing that with storage. They're used to ordering. They're used to using databases. And in memory, they're used to the order of things becoming visible in a certain order because x86 has a very strict set of rules about how things become visible. What they're not used to is having the memory rules apply to persistent memory. And so it is tricky, and we often enforce memory, persistent memory ordering by having flushing barriers in between the operations. So in my example, if you need to first store, somebody's new bank balance before you store the bit that says I completed this transaction, then you have to do the flush of one thing before you even start modifying the second thing. And so we spend a lot of time in PMDK, dealing with these ordering rules and making sure that we make our transactions as optimal as possible. But it is tricky. It's tricky programming. It's really why we created the library.
One, I think, last question before we hand it off to Steve.
Yeah.
If we don't have Optane, can we run these examples on a supported Linux or other OSs, for example, using hard drives or SSDs?
Yeah, they'll run on traditional storage, in fact, because PMDK will notice if the file that you give it is not real persistent memory, it will notice that, and it'll never use optimized flush. It'll just use msync. They'll slow down because they're not persistent memory, but they'll run just fine. So you can run them on your laptop. You can run them on any machine. And then if you want to try and run them on, instead of storage, on a kind of emulated persistent memory, it's actually quite common for people to just use DRAM and just tell Linux to expose it as persistent memory. We have instructions on how to do that on pmem.io. Just look in the documentation section. Steve Scargill wrote in some instructions there about how to emulate persistent memory, so you can do it that way too.
Thanks, Andy. Steve, you can take it on.